So just when you thought you understood how to draw a Lewis diagram, your teacher springs an exception on you, and it's called an expanded octet. In this video, I'm going to attempt to make it crystal clear to you what an expanded octet is, when it's okay to have one, when it's not okay, and of course the underlying concept behind this idea. If you'd be so kind as to like the video and consider subscribing to the channel, that would be greatly appreciated. My name is Neil, and I'm looking forward to helping you with this topic. Okay, let's begin with the octet rule. Octet means 8. As you can see behind me, the central atom in this molecule is surrounded by 8 valence electrons, 6 of them in the form of single bonds, and 1 lone pair which represents 2 electrons. In almost every Lewis structure, the octet rule applies. In other words, atoms are bonding with other atoms so as to have a complete outer energy level, which basically means they have the same number of valence electrons as the nearest noble gas. And again, most often this is 8. So when is it okay, or why is it okay, for there to be an exception to this rule? What is an expanded octet? This is an expanded octet. In the Lewis structure for sulfate, the polyatomic ion, we see the central atom, sulfur, surrounded by 12 valence electrons. We've got 4 valence electrons in each double bond and 2 valence electrons in each single bond. So why is this okay? We are far exceeding the octet rule. It turns out that some elements like sulfur and phosphorus, including a host of others, are able to accommodate these extra valence electrons. Why is that so? Where do these extra electrons go? And how do we know when to use an expanded octet? I want you to think back to when you learned about electron configurations. If you recall, as we're filling up energy levels and sublevels, working from the ones closest to the nucleus to the ones further away, we noticed a pattern. And that pattern was that there are only S and P sublevels in the first 2 energy levels. But all of a sudden, when we get to the 3rd energy level, we start to include the D sublevel. This was a larger sublevel that can accommodate 10 electrons. It turns out that nonmetals like phosphorus and sulfur, as 2 examples, because they have 3 energy levels, they have a D sublevel that's unoccupied. In other words, an empty space where more valence electrons can be stored. So the rule is, any nonmetal atom that has 3 or more energy levels in its electron configuration is able and possible to have an expanded octet situation. Okay, let's look at a practice question and see if you can answer it. At this point in the video, I just want to check for comprehension to make sure you're following along. Behind me on the board, you'll see 4 nonmetal atoms. I want you to think about which of these, if any, would be able to accommodate or have an expanded octet if it was the central atom in a Lewis structure. Think about that question, come up with some answers, and return to the video to see what the correct answers are. So hopefully you agree that out of the 4 options, only bromine and phosphorus are capable of having an expanded octet situation. Of course, this is because when we look at the electron configurations of the elements in question, only these 2 have 3 or more energy levels, which means they have unoccupied or empty D sublevels where those extra electrons can be stored. I think the hardest thing about expanded octets, the question I hear most often is, I just don't know when to use one. When is it okay? When is it necessary? How do I know if an expanded octet is better than a regular octet? In order to help you understand that, I've drawn 2 options on the board for the Lewis structure for phosphate. One where it has an expanded octet, in this case 10 electrons around the phosphorus, and in the other picture you'll see that it has a more standard octet with only 8. Now technically both of these Lewis structures work. They both use 32 valence electrons. They both have the correct atom in the center of the Lewis structure. But what's the difference really? And why would I say that the expanded octet is preferable to the regular octet? Okay, so in order to know the difference, in order to know when an expanded octet is going to work better for you, you really need to understand the concept of formal charge. And of course, I do have a video on that if it's something you need extra help with. When we look at the formal charges of the atoms in these two Lewis structures, it becomes clear to us that this Lewis structure with the expanded octet is more advantageous. It's preferable. It's the better drawing. Okay, why is that? Well, as you may know with formal charge, we love it when formal charge numbers are lower, closer to 0. In this example, we see 2 out of the 5 atoms have a formal charge of 0, where in the regular octet example, none of the formal charges are zeros. So overall, I would use formal charge as a tool to distinguish whether an expanded octet or a regular octet is the better option when comparing two Lewis structures. All right, I hope you guys found this video helpful, but don't be shy if you're still confused. Leave a comment below and I'll be sure to respond to you with some extra help on this expanded octet concept. Thanks for watching. Follow me on Instagram for updates about upcoming videos, and I hope you have a great day.